Money transfers were just one of a growing number of applications which required encryption to remain secure. And as the internet grew to encompass millions around the world, a new problem emerged. At the time, encryption required two parties to first share a secret random number known as a key. So how could two people who have never met agree on a secret shared key without letting Eve, who is always listening, also obtain a copy? In 1976, Whitfield Diffie and Martin Hellman devised an amazing trick to do this. First, let's explore how this trick is done using colors. How could Alice and Bob agree on a secret color without Eve finding it out? The trick is based on two facts. 1. It's easy to mix two colors together to make a third color. And 2. Given a mixed color, it's hard to reverse it in order to find the exact original colors. This is the basis for a lock. Easy in one direction, hard in the reverse direction. This is known as a one-way function. Now, the solution works as follows. First, they agree publicly on a starting color, say yellow. Next, Alice and Bob both randomly select private colors and mix them into the public yellow in order to disguise their private colors. Now, Alice keeps her private color and sends her mixture to Bob, and Bob keeps his private color and sends his mixture to Alice. Now the heart of the trick. Alice and Bob add their private colors to the other person's mixture and arrived at a shared secret color. Notice how Eve is unable to determine this exact color since she needs one of their private colors to do so. And that is the trick. Now, to do this with numbers, we need a numerical procedure, which is easy in one direction and hard in the other. Now, this is our solution. First, Alice and Bob agree publicly on a prime modulus and a generator. In this case, 17 and 3. Then, Alice selects a private random number, say 15, and calculates 3 to the power 15 mod 17, and sends this result publicly to Bob. Then Bob selects his private random number, say 13, and calculates 3 to the power 13 mod 17, and sends this result publicly to Alice. And now the heart of the trick. Alice takes Bob's public result and raises it to the power of her private number to obtain the shared secret, which in this case is 10. Bob takes Alice's public result and raises it to the power of his private number, resulting in the same shared secret. Notice they did the same calculation, though it may not look like it at first. Consider Alice. The 12 she received from Bob was calculated as 3 to the power 13 mod 17. So her calculation was the same as 3 to the power 13 to the power 15 mod 17. Now consider Bob. The 6 he received from Alice was calculated as 3 to the power 15 mod 17. So his calculation was the same as 3 to the power 15 to the power 13. Notice they did the same calculation with the exponents in a different order. When you flip the exponent, the result doesn't change. So they both calculated 3 raised to the power of their private numbers. Without one of these private numbers, 15 or 13, Eve will not be able to find the solution. And this is how it's done. While Eve is stuck grinding away at the discrete logarithm problem, and with large enough numbers, we can say it's practically impossible for her to break the encryption in a reasonable amount of time. This solves the key exchange problem. It can be used in conjunction with a pseudo-random generator to encrypt messages between people who have never met.